Hello everyone, welcome to my video on elementary differential equations. This is video number 5 for chapter 6, and the topic for the chapter is systems of two linear differential equations. In this video, we'll go through a few theoretical aspects of a system of linear equation, or in the abstract setting. Okay, so let's get started. So the general form of a system of first-order equation can be written in the matrix vector form as follows. So here, x is a vector, is the unknown, and then x prime is the derivative of the vector with respect to t, and p here is a matrix. If x vector is of size n, then this is an n times n square matrix. And then G here is a vector of the same length as x. Okay, so these here, they are both given. So the equation is the following. The derivative of x vector equals to a matrix times the x vector plus some given vector. In the special case where this G term here is identically 0, that it's not here, we call this equation a homogeneous equation. In this case, you can write it as x prime equals p times x, where p is a coefficient matrix. So in this chapter, we will only consider this homogeneous case. Let's first review the principle of superposition. This principle we have encountered earlier in the study of linear differential equation and homogeneous. Okay, and the same thing applies to systems. So let now have x1 and x2 both be solutions to this homogeneous equation above here. We call it H. Then you can make any linear combination of these two solutions. They are both vector valued. So you do a scalar multiple with the first one and a scalar multiple with the second one, and you add them up, and that's a linear combination. For any C1 and C2 arbitrary constant, this is also a solution. Now let's introduce the concept of the Wronskian, which we have also encountered earlier. And now we define this for a set of vector valued function. Let's say we have x is a vector valued function. So for each xi, it's a vector valued function. Let's say with length n. And then you have n of such functions. And the Wronskian of this is computed as the determinant of the matrix, we call it capital X. Here the matrix X is simply a matrix whose columns are exactly these vectors. Okay, so these are column vectors. x1 has length n, x2 has length n, and then xn has length n, and exactly this forms a square matrix of size n times n. And you compute the determinant of this, and that is called the Varonskin of this set of vector valued functions. So again, this Varonskin can be used to determine if the set of functions is linearly independent. If the determinant of this is not 0, then this set of vectors, n of them, is called a set of linearly independent functions. And that is what we wish to have when we want to form solutions. Okay, so if you now manage to find a set of linearly independent solutions, like that, x1, x2 to xn, and then we call this a fundamental set of solutions. So very similar terminology to second-order equations we studied earlier. And once you have this set of solutions, then you can use that to form the general solution. The general solution is just the linear combination of these, which is the following. You take each solution and multiply by an arbitrary constant, and then you add them all up. Okay. So this property suggests the following solution strategy for systems of first order system of linear equations and homogeneous. That is, we will aim at finding n linearly independent solutions, x1, x2 to xn, if it's a system of order n, and we verify those n solutions are linearly independent, and then we can use it to form the general solution. Okay, so this short video ends here. We'll just touch up on these few theoretical aspects, and in the next video we will start talking about solving linear system of ODEs. So I hope you enjoyed this, and see you next time.